Okay, so let's get started. Welcome everyone to this online conference on applications of Macdonald polynomials. So we have a lineup of very interesting talks spanning the whole week. Very first speaker will be Puska from University of Queensland, who will speak about the affine Casselman-Shalika formula and Macdonald's constant. Anna.
Thank you very much for the invitation to the conference. I'm very excited for the lineup of talks, and thank you also for the opportunity to speak. So I will talk about a topic that relates to Macdonald polynomials in sort of two curious ways, some of which we'll hear perhaps more about later in the week. First, I would like to talk a little bit about Whittaker functions and Iwahori-Whittaker functions, which are objects that I think about in the metaplectic context and in the infinite dimensional setting. And I will talk about how these relate to Macdonald polynomials and what are some interesting questions that one can examine about them. And then for most of the talk, I will focus on one particular way in which the infinite dimensional formula for these Whittaker functions involves Macdonald's constant term. So for now, let G be a group over some local field. If you like, you can always just think of the general linear group defined over p-adic numbers. But really, Whittaker functions make sense in a lot more generality than this. So you can think of any reductive algebraic group over even the reals. This is the case that is most interesting to me. So non-Archimedean local field. So Whittaker function is a function on this group that has some complex values. Classically, if someone said to Whittaker what a Whittaker function is, it is some analog of a Bessel function. It is determined on this group by certain invariance properties and the character of the additive group of the ground field. For number theorists, these functions are interesting because they can be used to define L functions associated to automorphic forms. So one studies Whittaker functions because one is interested in automorphic forms or automorphic representation theory. But that is sort of not as relevant to us right now beyond the motivation. And importantly, a formula by Shintani in the general linear case and Casselman-Shalika more generally expresses a Whittaker function as a multivariate polynomial. Now, this formula that I've put here might look a little esoteric. Essentially, what's true is that because of the invariance properties defined by or satisfied by a Whittaker function, it's enough to specify it on a maximal torus. So for example, if we're working with GL R+1 on diagonal matrices. And then these diagonal matrices over p-adic numbers have a very particular shape. So essentially a Whittaker function corresponds to points of a lattice, of a co-weight lattice. And the values of it can be expressed as a multivariate polynomial so an element of the group algebra of the co-weight lattice, essentially. So here, I just mentioned now that something that appears is a character of a representation, of a highest weight representation of some Langlands dual group. Anyway, Whittaker functions are multivariate polynomials for our purposes. Okay. Now, there are various ways to generalize this classical setting that was first motivated by number theory. So if n is a positive integer and mu n is the group of nth roots of unity, then we can change the group from a reductive algebraic group to a so-called metaplectic cover, which is a central extension by this group of nth roots of unity. And it's no longer an algebraic group. The multiplication law involves some arithmetic information about the ground field. And turns out that one can define Whittaker functions on these metaplectic covers by work of Kasdan and Peterson. And these are similarly useful for number theoretic purposes. So if one wishes to understand the meromorphic continuation and functional equations of so-called multiple Dirichlet series, which are in some sense multivariate analogues of Dirichlet L functions, then these are similarly useful to how the classical non-metaplectic Whittaker functions are useful in automorphic theory. Okay, so this is one direction. So we can take a Whittaker function classically on a reductive algebraic group. So this is the n=1 case. Or one can talk about them on a metaplectic cover of such a group. Or one can generalize in a different direction, and this will be very interesting to us, to a loop group, or even more generally, a Kac-Moody group. So the structure of the reductive algebraic group is very well understood in terms of some root datum, some Cartan data, and relaxing the conditions on the Cartan matrix, one can get a more general family of groups where now the underlying Lie algebra is infinite dimensional. And then, of course, one can combine these two directions of generalizations, and one can talk about Whittaker functions on metaplectic Kac-Moody groups. Okay. Please, by the way, at any time, interrupt if you have questions. Okay, so since in these cases, some of these cases, the Whittaker functions have similar number theoretic uses. A question that one must ask is, well, how to generalize this important formula, the Shintani-Casselman-Shalika formula, to these more general settings. And when it comes to the metaplectic generalization, sort of two different approaches to doing this have emerged. One way is, well, the Casselman-Shalika formula has this while character in it. By the while character formula, this can be written as a sum over the while group, corresponding to the reductive group. Well, in this formula, for the writing this character in terms of the while character formula, one can change the action of the while group on polynomials, on this polynomial ring, to the Chintaganel's action, and averaging using this action, in fact, similarly to the non-metaplectic case, produces the metaplectic Whittaker function. There's also a very interesting other branch of ways to try and generalize the Casselman-Shalika formula, and that is to produce the right-hand side as a sum using some statistics over a combinatorial structure. For example, by work of Brubaker, Bump, and Friedberg, one can do this as a sum over a highest weight crystal. There's also sort of other approaches to doing this, for example, using ice models from statistical mechanics. And then, interestingly, the action of the Iwahori-Whittaker algebra, the reductive group, can be used both to understand the connection between these two separate approaches to generalizing the Casselman-Shalika formula, and then to generalize further to the infinite dimensional Kac-Moody setting, metaplectic or not. It can also be used to construct so-called Iwahori-Whittaker functions, which I'll say more about in a moment, and in fact to see the connection to Macdonald polynomials. So I will talk a little bit more about what Iwahori-Whittaker functions are and how this Iwahori-Whittaker algebra comes into play here. So Iwahori-Whittaker functions, well, combinatorially, we can think about them as a refinement of Whittaker functions indexed by the while group. From a number theoretic perspective, another way of thinking about this is one can think of a Whittaker function as the value of some functional on a vector in a representation. And then instead of for example, taking a spherical Whittaker function, like plugging in a spherical vector into a functional, one can plug in a while group indexed set of Iwahori fixed vectors. So a certain finite set that is interesting. But sort of just looking at it algebraically, a Whittaker function can be decomposed as a sum over a while group into Iwahori-Whittaker functions. So in the classical setting, the non-metaplectic setting, by work of Brubaker, Bump, and Licata, these Iwahori-Whittaker functions can be expressed in terms of Demazure-Lusztig operators, TW. So these operators behave like generators of the Iwahori-Whittaker algebra. So when you think of some, they have some quadratic relations and braid relations that are very familiar to many of you, I'm sure. And then interestingly, through this appears in this paper by Brubaker, Bump, Licata, but uses a result of Bogdan Ion. These Iwahori-Whittaker functions are related to nonsymmetric Macdonald polynomials at the limit q goes to 0. And this q here is the Macdonald q, not the p-adic q, which would be the order of a residue field. And so I've committed a crime because the q that is whose limit is 0 here is not the q in the first formula on this page. But my excuse is that it is I believe it is the q that is the Macdonald polynomial q. So maybe that's more helpful to this audience. So the Demazure-Lusztig operators give a representation of the Iwahori-Whittaker algebra on the group algebra of the co-weight lattice. And in fact, they have metaplectic analogues. We proved this with Gautam Chinta and Paul Gunnels that satisfy similar relations and also give sort of a metaplectic representation of the Iwahori-Whittaker algebra on the co-weight lattice. And in fact, one can prove some interesting character formulas in this setting. We will, I think, hear more about this sort of metaplectic representations of the Iwahori-Whittaker algebra on Tuesday in Professor Sahi's talk, which is also a very interesting topic and sort of a very interesting way of relating, sort of coming up with metaplectic analogues of Macdonald polynomials. So these metaplectic Demazure-Lusztig operators are very useful, as I mentioned, in connecting combinatorial constructions of the metaplectic Whittaker functions. So on the one hand, I mentioned that one can think of this averaging in terms of the Chinta-Gunnels action. Now, through these operators, that can be connected to, well, a sum of these Demazure-Lusztig operators. I'm going to call this sum of TW a Hecke symmetrizer. And then this, in turn, can be related to that combinatorial sum over a highest weight crystal. Essentially, because Iwahori-Whittaker functions are refinements of Whittaker functions, they're much better suited to proving things because sort of the steps between them are smaller, roughly speaking. So somehow, like stepping from one Iwahori-Whittaker function to the next is just a matter of applying a simple reflection. And so applying an operator corresponding to a simple reflection is not as hard as, well, stepping from one rank to the next. Okay. So in joint work with Manish Patnaik, we showed that well, Iwahori-Whittaker functions, the number theoretic objects, satisfy a recursion in terms of these metaplectic Demazure-Lusztig operators. We've also constructed a metaplectic cover of Kac-Moody groups and extended the metaplectic Casselman-Shalika formula to this setting. So now again, we have a pretty terrible looking formula here, but I aim to convince you that this formula isn't so bad if you're already on board with the formulas on the previous pages. So what this is here, on the left-hand side, we have a metaplectic Whittaker, well, a Whittaker function defined on the metaplectic Kac-Moody group. On the right-hand side, this big sum is the analog of a wildcat's character. So the character of a highest weight representation. This wild group action that appears here is the metaplectic Chintagonals action. And well, this delta is just a sort of a deformed wild denominator, something similar to a Macdonald kernel that also appears in the finite dimensional setting. But there's a new feature that didn't appear in the finite dimensional setting, and that's this blue M factor here. So this correction factor is new. So what is this correction factor? Well, roughly speaking, the reason that it appears in, again, the infinite dimensional, so Kac-Moody generalization of the Casselman-Shalika formula, by the way, also in the non-metaplectic setting, not just in the metaplectic one, it appears essentially because when one wants to relate this wild group symmetric wildcat's character to a Hecke symmetrizer, so this sum of Demazure-Lusztig operators, then in the infinite dimensional setting, to relate these two, one needs this extra factor. So I just want to mention that in the finite setting, this element on the left-hand side is an element of a Hecke algebra. In the infinite dimensional setting, this is an infinite sum. So it's a bit harder to work with, but very possible to work with. One just has to be a bit careful. Okay, so strangely, this relates to Macdonald's identity. So if one takes this wild symmetrizer of this 1 minus t e alpha over 1 minus e alpha product over positive roots, then there's this beautiful identity that relates this to the Poincare polynomial of the wild group. This works for any finite root system. However, for Kac-Moody root systems, this formula doesn't hold as written, but it does hold if one inserts the correction factor m, this blue m, on the left-hand side. Strangely, this is the same m that appears upstairs in the Casselman-Shalika formula. So this m can also be expressed from the norm used to define Macdonald polynomials, right? It's sort of the a constant term of that norm in some sense. Are there any questions so far?
So I would usually, can I ask, I would usually like to write such factors as products of C functions over some roots. Does it have a C function? The M have a C function product?
Oh, I can, you mean, can I write it as a product over like a root cone or something like that?
Yeah. Product of C functions over some root cone. Yeah. Okay, great.
Yes,
Thank you.
yes, and yes, indeed, and in fact, that is the form that I will be interested in. How I would like to write this always. If I'm thinking of the correct thing, well, we'll see in a moment.
Okay, thanks.
Yes, thank you for the question. Okay, so just in case you aren't as excited about Whittaker functions on Kac-Moody groups as I am, I want to say that this this correction factor also appears in other instances where one wants to take a formula from p-adic representation theory and extend it from the finite setting to the affine or Kac-Moody generality. So for example, Macdonald's formula for the spherical function involves the same correction factor m when one wishes to write this down in the infinite dimensional setting. This is by work of Braverman, Kazhdan, and Patnaik in the affine setting. and Bardipans, Gossan, and Rousseau more generally. So taking the limit in lambda, this converges to the Gindekin-Karpelovich formula. And again, in the infinite dimensional setting, M persists. This is by work of Braverman, Garland, Kazan, and Patnaik, and then also Ebert and Auguste Ebert and Abid Ali in the Kac-Moody generality. Interestingly, well, perhaps not surprisingly to some of you, this is also related to Dolbeault cohomology. Macdonald's formula can be computed by computing Dolbeault cohomology and Betti cohomology. And then somehow the identity comes from the fact that these two are equal by the Hodge theorem. And somehow the failure of the Hodge theorem in the affine setting is measured by this correction factor M. So Fischel, Grojnowski, and Telemann have, when they compute the Dolbeault cohomology of an affine Grassmannian, then they kind of prove a strong Macdonald conjecture and kind of get a stronger, like a deformation of this correction factor M. Okay, so for the rest of the talk, I would like to talk about some joint work with Dinakar Muthiah and Ian Whitehead, studying this correction factor M in Kac-Moody generality, so beyond the affine setting. And generally, what we want to do is write this M as a product over the imaginary root cone, and to every imaginary root, we will have a product of factors of the form 1 minus t to the n e to the lambda, where lambda is this element of the imaginary root cone, is all I will say for now. And then this factor appears with some multiplicity. And then for a fixed, so this is over the positive imaginary root cone. And then these coefficients m lambda n can be, for a fixed lambda, collected into a polynomial. And so this is the polynomial that we will be interested in computing. Their constant term is the multiplicity of an imaginary root. So there is this interesting correction factor M that pops up anytime one wants to write down a formula from p-adic representation theory, but for Kac-Moody groups. And it's constant. It's sort of if one writes it as a product like this, then these polynomials derived from it have the constant term, have the imaginary root multiplicities as their constant term. Okay. So if there are no questions about this so far, then I will say a bit more about how one gets a handle on this polynomial, on this correction factor, and what one knows about this in the affine setting already, and then later on what one can say in further generality. Please again interrupt if you have questions. Right. So in the Kac-Moody generality, we wish to define the correction factor M exactly by this formula that's true in the affine setting by Macdonald's work. Right. So this is somehow the natural way that M appears is by relating the Poincare series of a Weil group to a Weil symmetrizer of this delta kernel. So just sorry, here delta real is a product over positive real roots of this 1 minus e to the alpha, and then delta t real is just a deformation with t, and again pt is the Poincare series of the Weil group, which is now infinite. Okay, so in order to talk about this object, one has to consider, well, the positive root cone and the positive imaginary root cone, which are cones graded by height, And then one can talk about Lorentz series on these cones, and in particular, Lorentz series, a ring of Lorentz series and the units in them, which all have the form, all have this form as a product. And well, one has to be careful about acting on this with the while group. It doesn't quite make sense to talk about the action of, it's not so easy to talk about the action of the while group on the entire Lorentz series ring, but the while group does act nicely on a multiplicative subset containing this delta T real over delta real factor that we want in this formula. So one can show that in the appropriate ring, this sum on the left-hand side of this formula, so this while average of this delta over delta is a unit who's in this power series ring that's regular in the proper sense, and its constant coefficient is the Poincare series. Okay, so this is a lot of technicalities to be able to talk about M in a reasonable way. And so now we may define M as the thing that makes this highlighted equation true. It is while invariant, that's easy to see from this, and therefore supported, well, because the sum on the left-hand side has constant term, that is the Poincare series, M is supported on the positive imaginary root cone. And then both M and its inverse are Lorentz series units and have constant coefficient 1. And furthermore, M inverse is the inverse with respect to the positive imaginary root cone of delta real over delta T real. So I just want to briefly illustrate this. So just a comment that this is a lot nicer in the affine type. M, in some sense, is a single variable power series on the in the affine type, because I mean all the imaginary, well, the imaginary positive imaginary root cone looks very simple. It's just multiples of some delta minimal imaginary root. But if we go, for example, to further generality, so for example, to this hyperbolic type, then M is no longer supported on a single line, but instead on the positive imaginary root cone, pictured as the blue dots here. And well, there are some further difficulties when one moves beyond the affine type. One is that, well, we have this formula that M inverse and delta real over delta T real. Remember, this is some product over positive roots. These are inverses with respect to the positive imaginary cone. In the affine case, this implies this constant term property of M, that it's just sort of if we restrict this quotient to the positive imaginary, to multiples of delta, then we just get M exactly. This is not true in the Kac-Moody case. Essentially, the reason it's not true is because just having the support of some power series A contained in the imaginary root cone doesn't mean that if we multiply A times B and restrict to the imaginary root cone, that's the same as first restricting and then multiplying by A. Right? So multiplying by a purely imaginary series cannot be cannot be exchanged with restricting to the positive imaginary root cone. Perhaps it's easier to see this with a picture. I can get an imaginary root as a sum of a real root and an imaginary root. in the beyond the affine types. Well, this of course doesn't happen in an affine type. Okay, so in the affine setting, so for affine Kac-Moody groups, Cherednik's solution of Macdonald's constant term conjecture tells us what M is exactly. So for untwisted simply laced affine types, M can be written as this product. Well, where here R is the rank and Mj are the exponents of the underlying finite dimensional root system, and delta is the minimal imaginary root. So I want to write this in a slightly different way, which is the same product, I promise. As a product from I goes from 1 to infinity of, well, factors where I have 1 minus t to the k times e to the I delta squared in the numerator, and then in the denominator I have factors where the power of t is 1 less and 1 more. So what this boils down to is that if I write down that this sort of polynomial corresponding to a single imaginary root, I delta, then I will have in this polynomial factors of the form of -1 plus 2t minus t squared. So somehow the t to the k minus 1 term here turns into this -1 times t to the k minus 1. And then the t to the k factor squared turns into this plus 2t. And then this other thing, the second thing in the denominator, the 1 minus t to the k plus 1 factor turns into this -t squared. So what I find is that these polynomials associated to a single imaginary root are divisible by 1 minus t squared. And in fact, what's left of the polynomial says something about the affine Lie algebra. Or perhaps I should say the root system of the affine Lie algebra. So more generally, by work of Cherednik and Macdonald, for any affine root system, not just the simply laced ones, M can be written as, again, a product over the positive imaginary roots. And for each lambda imaginary root, we have a product that looks very similar. So I have a factor corresponding to some power of t in the numerator, and it's squared. And then the off by 1 powers of t factors appear in the denominator. So this S lambda is somehow one can choose a finite root subsystem of the root system, and for any imaginary root, one can see, well, what finite roots can I use to translate this into a real root? And if I take the heights of the roots in that set, those are exactly the heights that appear in this product. So this polynomial of t associated to the imaginary root will be, again, divisible by 1 minus t squared. And then if I divide out by 1 minus t squared, then what's left is somehow a collection of these heights. Are there any questions at this point? So the the reason I mentioned this is because intriguingly, some of this, so this 1 minus divisibility by 1 minus t squared will generalize to the Kac-Moody setting. But it's the factor remaining after dividing out by that is very mysterious. One would expect that it has something to do with the Kac-Moody root system and the corresponding Lie algebra, but I don't know why. We'll come back to this in a moment. Okay. So this formula by work of Cherednik really says what M is in the affine setting. It's understood very well in some sense. But now, what can one do beyond the affine type? Well, essentially the theme of the couple of results that I'm going to mention is that, well, I've said that M is in some sense a deformation of the imaginary root multiplicities. So maybe some methods that we can use to compute imaginary root multiplicities will generalize into methods to compute M. Indeed, we'll see two examples of this. One is the Peterson algorithm, and then the other one is the Berman-Moody formula. Okay, so all right, we have this correction factor M. Well, I keep calling it as a correction factor because that's how one encounters it in p-adic representation theory. But anyway, we have this M that we've defined through some careful manipulating of Lorentz series units in some ring, and we can write it as a product over the positive imaginary root cone, and to each lambda element of this cone, I have a finite product of factors of the form 1 minus t to the n e to the lambda, with some exponent that depends on the exponent of t and the lambda place where we are. Okay, well, the goal is to compute all the coefficients corresponding to, all the exponents m lambda n corresponding to a fixed lambda. So one can do this starting from this formula for M inverse. So remember, this formula says that M inverse is a power series inverse of delta real over delta t real with respect to this imaginary root cone. So what that means is exactly what I've written here, that the product restricted to the imaginary root cone is trivial. So using this, one can compute the coefficients m lambda n by induction on the height of lambda. This is something that can be coded in Sage, for example. The algorithm is polynomial in the height of lambda in terms of the simple roots. And as I mentioned, it is a generalization of the Peterson algorithm to compute imaginary root multiplicities. And well, when one tries to code this, one soon figures out that one can do a little bit less work than at first it seems, because it suffices to compute it once per W orbit by while orbit, for example, on the anti-dominant cone, because as I mentioned, M, from the way it's defined, it's Weyl group invariant. Right? So, for example, in this picture that we've seen earlier, we want to compute what a polynomial from these exponents for every blue dot. So using this generalized Peterson algorithm, we can do that sort of one gray line at a time. And for example, on this blue dot here, all we need to know is the values of the polynomials for on the blue dots on previous gray lines, and then also what the real roots are up to that height. So that's an ingredient. But because at first it seems that one has to do this for all of these blue dots separately, but in fact, all of these bigger blue dots are on the same Weyl orbit. So it's enough to do it for this first one, and then one gets a couple of values of these for free. Okay. So another thing that one can generalize from computing imaginary root multiplicities in the Kac-Moody setting to computing M is the Berman-Moody formula. So this formula again looks quite intricate. Its purpose is not so well. The previous algorithm I've mentioned, the generalized Peterson algorithm, is very useful if you want to just get some data to look at. If you want to sort of think about some question relating to this correction factor M in the Kac-Moody setting, you can quickly produce some data by coding the previous algorithm in Sage, for example. The significance of this is more from a theoretical perspective. So as I mentioned, for t equals 0, this recovers the Berman-Moody formula for imaginary root multiplicities. And well, there's a lot of technical details. So this pair lambda is some vector partitions of the lambda element of the imaginary root cone. There's some multinomial coefficient here and the Möbius function, etc. The P that appears here is some modification of the Poincaré series given in terms of some constant partitions. But then using this formula, one can prove that the M has similar properties in the Kac-Moody setting as it does in the Affine setting, though those properties are a bit more mysterious in this context. So for example, I've shown that, so I've said that this M, the correction factor M was written as a product over the positive imaginary root cone. It's trivial outside of imaginary roots. So those polynomials I've associated that collect the exponents of that product form are 0 unless lambda is an imaginary root. And then it has various sort of good properties. For example, M restricts, as one would expect, to a root subsystem. If a root system is reducible into 2 orthogonal components, then the corresponding M's are sort of multiply. And then using these sort of simple facts, one can show that the polynomials M lambda t are again divisible by 1 minus t squared. So remember, this was in the affine setting, this was a consequence of that formula by Cherednik. So somehow in the affine setting, we knew that from the explicit formula for M, 1 minus t squared, negative 1 plus 2t minus t squared divides this M lambda t polynomial. And the quotient says something about heights of roots that can be used to translate lambda into the real portion of the root system. Well, in the Kac-Moody setting, one can prove this using this generalized Berman-Moody formula on the previous page. Here is a couple of words about how the proof goes, but we don't need to go into that. But what's interesting is that it's not clear what the rest of the polynomial is. So in the remaining few minutes, I would like to show you a couple of examples of M in the Kac-Moody setting, and what the quotient of this M lambda T by 1 minus T squared is. So I'm going to call that chi lambda T in some conflict with the very beginning of the talk. This is no longer a Kac-Moody, no longer a wild character. So using the generalized Peterson algorithm, one can compute this for some hyperbolic root systems, and I will show you illustrations of this for the ones with these Cartan matrices here. So 2 of them of rank 2 and one of rank 3, and I implore you to notice things because I mean, I would really like to understand what is this correction factor in Kac-Moody generality. For example, it would tell us more exactly, more sort of exact. It would give us more exact knowledge about these Kac-Moody analogues of p-adic representation theory formulas, like Macdonald's spherical function, or sorry, Macdonald's formula for the spherical function, or the Casselman-Shalika formula, etc. Okay. So first, Cartan matrix 2, -3, -2, 2. Well, the constant terms are the multiplicities of these imaginary roots. I'm sure you all know that by heart. What else? Well, it seems to be non-strictly alternating coefficients. And it goes on. So I mean, I've tried to only write down one element of every Weil orbit, as you can see from the fact that these are all different polynomials. But this alternating sign property goes on for, well, as far as we've checked. So in particular to polynomials where it's quite long. And it's the same for this other hyperbolic root system as well. Sadly, it is no longer true in rank 3. Here, 4, 5, 2 has this t cubed plus t squared portion. So, so this is utterly mysterious to me, and to my collaborators. Last I've checked. So there's a lot of questions that I would like to know the answer to. So, for example, these polynomials. So when I divide out by the 1 minus t squared, whose analog exists in the finite setting, then I'm all the time, all the places we've checked, these have alternating sign coefficients in rank 2 hyperbolic type. But I don't know what the coefficients mean in terms of the Kac-Moody Lie algebra. So I mean, first of all, I don't know that they have alternating sign. It just seems like that from the examples we've checked. I would like to know if that's true in general for rank 2 hyperbolic root systems. Furthermore, I mean, these, as I mentioned, these coefficients have a kind of an understandable meaning in terms of the root system for affine types, but I don't know why that's what the similar explanation is, or what the similar significance is for Kac-Moody algebras. I don't even have upper bounds for the degree and coefficients of this polynomial. They could be anything.
Upper bound means your capital N lambda? Is that what?
For the degree, yes. But also for the coefficients, I don't know anything about them. Like even for, if we knew that they were all quadratic polynomials, I don't know how to count the coefficients. And then, well, one can get a bit more fanciful with this. I mean, there's other families of polynomials, for example, Kac polynomials that are deformations of imaginary root multiplicities. I don't know if there's any relationship between m lambda t and these. And then, of course, if one, I'm told that if one could compute the Dolbeault cohomology of a Kac-Moody flag variety, then one would in fact get a 2-parameter generalization of M. So that is a harder question to answer, to computing the Dolbeault cohomology of a Kac-Moody flag variety, but it would in particular tell us what M is. Of course, on the other hand, I mean, that would be a harder question, but even giving an explicit formula for imaginary root multiplicities is as we know, not so easy. So M is stuck in between these two hard questions, I suppose. Thank you very much. That's all I wanted to say.
Okay, let's thank Anna for a nice talk. Any questions?
Go back to a slide that says a bit more than just thank you.
Do you have something? What is the meaning of 1 minus t squared? Do you have some?
So the one of the 1 minus t's is easy somehow. That's some easy limit of from the p-adic formulas. One can recover that. Beyond that, I don't know. I mean, beyond the fact that sort of this form of Cherednik's formula, I don't know what else the 1 minus t squared means. So again, just the 1 minus t divisibility is easy. One doesn't need, even in Kac-Moody generality, that's a simple specialization. But the second one, I mean, the only way we knew how to prove it is using this generalized Berman-Moody formula. And again, in the affine setting, sort of this formula might be familiar, but other than the shape of this formula, I don't know what the significance is.
So I guess I missed this, but is it easy to see that M is somehow supported in just the positive imaginary cone?
Oh, it's that's not hard because it sort of follows from the Weil group invariance. Or sorry, perhaps. Oh, sorry, I'm going the wrong way. Let me go to the definition of M. So sorry. So we use this formula here to the highlighted formula here to define M precisely in the Kac-Moody generality, and one can show that on the left-hand side, the sum over the Weil group is regular and does have the Poincare series as its constant term. So from the Weil invariance of both sides, it's clear that somehow M is not moved around by the Weil group, if that makes sense. So somehow, like, the fact that it's supported on imaginary roots comes from this fact. I think maybe that's the. I'm not sure if that's the best way of saying that, but yeah.
And another question: you don't really know anything about special values of this, the t deformations. I mean, at t equals 1 or any such thing.
Well, just that, I mean, the t equals 1, that it's 0. That's not hard to see sort of directly from I think even the p-adic formulas, or even I guess even from this one, perhaps if right. So the fact that for t equals 1 we get 0. Oh, sorry. I have to be careful here because so the fact that this m lambda t for t equals 0 gives the multiplicity That's not hard. But beyond that, no, I don't know.
So, I mean, there's other polynomial that you get after factoring out the 1 minus t square or whatever.
Yeah, so of those polynomials, I mean, we can compute them, but I don't know what they are. I mean, oh, sorry. Yeah. So we can compute them, but we don't recognize them as meaning something about the. I mean, they should somehow say something about the root system, but.
So I'm not. Maybe someone knows the answer. The Kac polynomials themselves are, I mean, some special values. So at t equals 1, the Kac polynomials have some known values. Is that right? Or, I mean, I'm just asking because you sort of posed the question of comparing these with the Kac polynomials. So I'm just wondering if they are any better known.
Yeah, I don't know. I mean, for t equals 0, they give the same thing, but I don't know for t. But sort of, I should say that for t equals 0, they give the same. They both give the root multiplicities, but that's sort of easy for M and very hard for the Kac polynomials. But I don't know for t equals 1.
Okay. Yeah.
I mean, nothing very direct at the very least, I think. Yeah. I might have to write this down and then maybe I could say something intelligent.
Thanks. Any other questions? Okay, so maybe if not, let's thank Anna again for the very nice
Thank
talk.
you very much for listening.
So just an announcement about the next talk. It will, I mean, the original schedule had a talk soon after this, but that will take place tomorrow by Fagin. And